In this video, I'd like to look at Mathematica or Wolfram Cloud, a parametric equation, and I chose the heart shape. So first I started by Googling parametric equation heart and got to this Wolfram MathWorld Wolfram.com page. And I decided to go with this shape here. And the image is sort of bad in that the equation for y is like missing the minus sign. So something went wrong in the capture there. But it's 13 cosine t minus 5 cosine 2t minus 2 cosine 3t minus cosine 4t. And the x is 16 a sine cubed. So those are the equations that I want to play with and plot them, make a parametric plot, and so on in Mathematica. Okay. So here is my notebook, and I start off with those two equations. So here I am, the x equation, 16 sine t cubed. And it's the sine that's cubed, not the sine of t that's cubed, not the t that's cubed. Okay, so that was that I entered, and then I also entered the y equation with, of course, the minus sign somewhere missing from the web page. Now, it just annoyed me slightly that one of the equations was cubing the sign, taking the sign to some power, and then the other one was using multiple angle formulas, and that's just sort of, in my mind, to some extent, like two different approaches. So you can get angle formulas into powers of trigonometric functions and vice versa. So I just sort of figured the two out. So here is which one was this? Here is a y of, oh yeah, here it is. So 12 sine of t, I should have called it t, but I switched from x to t for some reason. But 12 sine of the variable minus 4 times sine of 3 of the variable is equivalent to 16 sine t cubed. So I'm entering this other thing. No good reason to switch from x to t, but I did. Shift enter. Okay, and now I'm plotting two functions. So I'm doing a plot of two mathematical functions. Here is a list of two mathematical functions, my x of t, and this function, I re-entered it now as a function of t, and I'm plotting it from 0 to 2 pi with my t variable. And we see one equation, which means that the two equations lie on top of one another, that they are the same. And I can sort of show that if I come in here and add in just the teeniest little bit to sort of shift one away from the other. Maybe a little bit more. 0.1, is that enough to see? I'm on a scale of, it's going up to like 16 here. So there we go. So now I made enough of a change that you can see that they are, that there are two curves there, but without that shift, those two curves are the same curve. Okay, so this is just, if one preferred multiple angle formulas, then this is equivalent to 16 sine t cubed. And equivalently, here's my y of t that they gave us. And here's the equivalent function in terms of, powers of cosine. So minus 8 cosine of t to raise to the 4th, minus 8 cosine of t raised to the 3rd, minus 2 cosine of t squared, plus 19 cosine of t plus 4, or at y of t that they gave originally. And again, same curve. So one, their either approach works and what they gave, and I do agree that those are both simpler than the alternatives. So it does make a certain amount of sense. And so that's what the x looks like that's what the y looks like plotted from the full 0 to 2 pi. Here we are putting them together as a, so Mathematica has built in this thing called parametric plot. You say, here's my x and here's my y as a function of t, and I'm letting t go up to 2 pi. So this is that concept of a parametric plot. And there is that heart shape. So that was one thing I wanted to do, was play with a parametric plot in Mathematica. It's just a built-in method that they have. Okay. Now I wanted to, I'm not going to, but I might consider that I might like to scale this somehow and sort of know how far it expands every which way around an origin. So I said, find the minimum and maximum, but we'll find the maximum x. And that came up to be, so I put in FindMaximum as my function of x as function of t, and I just gave it, it's looking for a maximum in the vicinity of 1. I chose 1 fairly arbitrarily. So shift enter. And it came up that the maximum x is about 16 from the origin. So here you can see it's sort of going through 15, but it's still going to the right. And so it gets up to about 16 according to this. And that's probably something nice like pi on 2, right? Okay. Probably, I don't know. Well, let's see. What is numerical pi divided by 2? It's 1508, so pretty much pi on 2. Okay. I found the maximum y again at around 1, and that's coming up to be around 12 at a t close to 0.9. So that's probably up here. This is probably the 12, the y, the high y. The minimum is down here, and that's 17. So the x is symmetric, so the sort of max and min have the same sort of information for the most part, but the y is not, it's not symmetric about, it's not it's horizontally symmetric, it's not vertically symmetric. So it gets, this is the farthest point. It gets to be 17 from the origin. I think that is the farthest this thing gets from the origin. But since I'm interested in sort of how the maximum radially, I took x squared plus y squared square root. I took the radius and found its maximum. And that was this 16.888. And then I plotted the whole sine of x squared plus y squared for the whole 2 pi. And here's the minus 17 at the bottom. And then there are these other 2 points, this guy and the sort of the other guy on the other side, that are almost 17 away. So that's some point sort of in here, sort of a maximum that's about almost 17 away, 16.88 away. This is 17 away. So that just gives you an idea of the expanse of this equation. And if you wanted to scale it, you should know how far this equation goes. This goes up to 17, and that would give you an idea. Sort of just multiply everything. If you wanted a radius, if you wanted your farthest point to be not 17, but something else, then you know how to scale the equation. So that's just why I wanted to play with that in case I wanted to scale it at some point. Okay, so that was that game. That was me plotting the sort of radius, if you will. Okay, and then I decided to play one more game for fun. Here was the parametric plot. That was the game I wanted to play. And then, but I wanted to sort of see it sort of traced out in time. And that is Animate. And if I just animate the parametric plot, I had the problem that it was giving me the sort of plot range was big enough to draw as much of the function. So originally I had this as like an animate variable, and it size of the graph was changing, and I didn't like that. So now I made a fixed sort of parametric plot. So there is my parametric plot, but I added an epilogue of this blue dot. So this is something I'm adding to my graph. It's a blue dot. It's of a large size. And then I used my X and Y functions and I introduced a new parameter, S, so then it was independent of the T. So the T was the parametric plot parameter or variable. And then I used the same function, but a different parameter, S this time, and use the S for my animate parameter. And then you see the blue dot sort of tracing around, and I can sort of stop it and start it. I can make it go slower or faster, and I can reverse its direction. So let's slow it down a little bit. You can see it sort of that point, that XY point sort of like tracing out the parametric plot. So made me happy anyway. Okay, so that's what I wanted to show you, just the parametric plot, animate, a little bit of playing with FindMaximum, FindMinimum, just showing off some Mathematica's features. Thank you for your attention.